Okay, so I record the lectures. I do record the lectures and make them available for you. It takes a little time to process them to get the closed captions on, but all right. So once again, in Calculus 1, you ended that course by learning about finding antiderivatives, and this is a table from section 5.3 in your textbook. Thank you, Sean. This is a table in section 5.3 from your textbook, from your ebook, that has different antiderivative rules. So for instance, a polynomial. A polynomial is a function that you can find the antiderivative of. The exponential function, the integral of e to the x dx, that equals e to the x plus a constant. Okay, so you learned about integrals. You can find integrals of polynomials, some trigonometric functions, you know, and these are very common rules. So but the thing is, there's a lot of other antiderivatives we need to find where these rules alone will not help us. So we need to have some techniques to you know, help us do more complicated antiderivatives. All right, and that being said, we're going to learn section 5.5 about what's called the substitution rule. So now, what I like to do generally, how many of you like to, as examples are covered, like to take notes in your notebooks? All right, it's generally a good idea. Okay, Jacob likes that, and Audrey likes that. Okay, a lot of you like that. Okay, so what I'm going to do is I'm going to give you a chance to copy this example down. Okay, and then we'll go through the solution. And when I do the solution, you know, I'm going to use the pen here to highlight certain things. Generally, students find that helpful. So this is, Michelle likes that too. So this is really like you're in a class, right? I'm trying to make this remote class like a real class. Well, it is a real class, but I'm trying to make it like a face-to-face on-campus class the best I can. So, all right, so let me give you a moment to copy this example down. I'm right here, Samuel. Yep, so what I do is sometimes when students are copying, I mute things. I mute a little bit, but I'm here. So what makes this, you know, what makes this antiderivative kind of hard? I mean, I don't think you know offhand the antiderivative of this. The integral of 3x times the square root of 1 plus x squared dx. What kind of makes that a complicated antiderivative to find?
The square root.
The square root.
That's right, Sophie, the square root. So what we can do is we can say, all right, well, you know, like for instance, if I had the integral of the square root of u du, and hold on here, let me get my, one moment, let me get my stylus hooked in here. One moment. Okay, so if I had the integral of the square root of u du, let's just use the u there, That's the antiderivative. I mean, that's the integral of u to the half du. And then what's the antiderivative of u to the half du? Well, you're going to take the 1/2 power and add something. What are you going to add?
1.
1. That's right, Jacob. And then you divide by 1/2 plus 1. And then, of course, you have your constant of integration. And so what ends up happening is you have u to the 3/2 over 3/2 plus a constant. And that's going to be then 2/3 times u to the 3/2 plus a constant. So the idea is that the 1 plus x squared, if we had just like a u there, it would make our life, it might help us. Okay, so what we're going to do is we have to decide, okay, I'm going to make a change of variable. I'm going to let u equal 1 plus x squared. I'm going to see if that can get us out of trouble here. If we can find this antiderivative by making this here substitution. Okay, so given that, then let me go to the next page. Are there any questions so far? Okay. So first thing I do is I call this integral, I set it equal to I. Okay, it's generally a good idea to do that. Call the integral your I integral. And I'm making the substitution here, u equals 1 plus x squared. Okay. Now, if u equals 1 plus x squared, then du dx would equal 2x. The derivative of 1 plus x squared is equal to 2x. But if du dx equals 2x, then, I can du dx, that's a derivative, but that's a rate. So it's a quotient of two differentials. So I can multiply by dx on both sides. Hold on here. I can multiply by dx on both sides, and then I have that du equals 2x dx, because on the left side, the dx's simplify. And so du is equal to 2x dx. Now what am I trying to do here? Now what am I? Let me go back here a little bit and tell you what I'm trying to do. So what I got to do, I'm converting this integral is an integral with respect to x. I want to convert that integral to an integral with respect to u. So the 1 plus x squared that's going to equal u. But I still have this 3x times dx that I got to worry about. I got to replace that with a function of u also. And well, okay, well, since du is equal to 2 times x dx, then if I multiply both sides of that by 3/2, okay, which I do here, I multiply both sides of that equation by 3/2, then 3/2 du will equal 3x dx. And so now this integral here, which was with respect to x, I can rewrite that integral as this equivalent integral, the integral of the square root of u times 3/2 du. And this integral here is a much easier integral to work with. I can get that antiderivative, no problem. Okay, are there any questions? Are there any questions up to this step here? Please ask if you have a question, okay? Please ask. Questions are encouraged.
I have a question, Professor. Can you clarify where the 3/2 came from?
Okay, so why did I use 3/2? Well, okay, so good question, Nathan. I have a 3x times dx here. You know, this, if you think about like this integral is equal to a Riemann sum, right? And you take the limit of delta x and let that approach 0, right? Or, you know, so everything's being multiplied. All these terms are really, you can think of them as multiplied. So the 3x dx, well, I got to get 3x times dx. I have that du equals 2x dx. So if I take 2x and multiply it by 3/2, I'm going to get the 3x. That's why I chose 3/2. Because it was the right multiplier to get me 3x dx on the right-hand side of the equation.
Okay, that makes sense. Thank you.
Okay. Okay. All right, good. Okay, so then we're here. We're here now. And of course, constants, the 3/2, right? That's a constant. Constants can be pulled out in front of the integral sign, which you learned in Calculus 1. And now I have in the integral of u to the 1/2 du. The antiderivative of u to the 1/2 is equal to 2/3 times u to the 3/2. Of course, we have our constant of integration because this is an indefinite integral. Well, 3/2 times 2/3 just gives me then a 1. So I end up with, you know, my integral is u to the 3/2 plus a constant. But let's keep in mind that our integral I here, hold on here, our integral I was equal, I mean, originally it was this integral. So the antiderivative, since the integral is with respect to x, the antiderivative has to be with respect to x. So what I do then is the u now, you know, basically with this step here, I found my antiderivative, but now I gotta substitute back in the 1 plus x squared for u. And so it turns out that the antiderivative of 3x times the square root of 1 plus x squared dx, that's just going to equal 1 plus x squared to the 3/2 plus a constant. Now you can check this, right? You can check it by taking the derivative of 1 plus x squared to the 3/2 plus constant. So you're taking the derivative of the whole thing here. Well, by the chain rule, right? This is 3 halves here. By the chain rule, you're going to get 3 halves times 1 plus x squared to the 1 half times 2x. And that's just going to equal x times the square root. That's going to equal 3x times the square root of 1 plus x squared. So in other words, when you take the derivative of your antiderivative, you get the integrand back. How many remember doing that for, checking to check that your antiderivatives are correct? You take the derivative of the antiderivative and see if you get the integrand back. How many remember doing that from Calculus 1? Okay, Jacob remembers it. Sean remembers it. And Maria remembers it. And thank you, everybody, and Leping. And I always I name as many names as I can, I appreciate participation. So yeah, that's the right antiderivative. We got it. We got so this here is correct. And you can always do a check. Are there any questions on this problem before we move on to the next one? We're gonna try to do some different examples for substitution. And actually here, class, let me just go to the next page. This here is what I just sort of showed you in that with the marker here. So you're welcome to copy that if you want. And I'll give you a moment here. Let me know if you have any questions. All right. If there are no questions, yes, question? Yes, Bob.
I have a quick question about the check part. This is on the first line on the right-hand side of the equation where it says 2x plus 0. Where did you get that?
Oh, okay. So, all right. Let me see here. So this here, you have an inner function, 1 plus x squared, and you have an outer function, the 3 halves power. So when you take the derivative of that, you have to use the chain rule. So remember the chain rule? Remember if you have...
I think I get it. You took the derivative of the x squared, and that gave you 2x, and the zeros for the derivative
exactly right. That's exactly right. The derivative of something to the 3 halves power is 3 halves times 1 plus x squared to the 1 half. And then the derivative of 1 plus x squared is the 2x. And then the derivative of that constant is just 0. The derivative of a constant equals 0. And yep, that's right. That's right.
Thank you, Professor.
Sure. Are there any other good questions? Okay. All right, well, let's move to another example here. Okay, let me give you a moment to copy this one down. Okay, so let's see here. Now this one, this integral, what makes what makes this integral here complicated? We always have to think about that because we got to decide, you know, what is our u substitution going to be? What makes this complicated?
The sign?
The sign. That's right, Tal. The sign of that x to the 16th power. You know, can we integrate the sign function? Did we learn that? What's the antiderivative of sine?
Cosine?
Cosine?
Cosine.
Let me see here. I should know that. Hold on. One moment. Hold on. I don't want to answer too quickly. How about negative cosine? The antiderivative of cosine is sine, but the antiderivative of sine is, how many remember negative cosine?
Yeah, negative cosine.
Yes.
Negative cosine. Okay. All right. So if we had just the sign of like u instead of that x to the 16th, that would be good. So that's telling me maybe I should consider a substitution where I let u equal x to the 16th power. Okay. So let's go ahead to the solution and see if that works. Okay, so I'm going to let u equal x to the 16th power. Okay, so that means in my integral, the x to the 16th power is accounted for. That's going to be u. Okay, so what's left then? What's left is the x to the 15th and the dx. I gotta write that as a function of u also. Okay, well, if u is x to the 16th, then du dx would be, by the power rule, 16 times x to the 15th. Well, I have just an x to the 15th here. Okay, well, first of all, again, if du dx equals 16 times x to the 15th, then if I multiply, hold on here, if I multiply, no, I don't want that, hold on. If I multiply both sides of this equation by dx, okay, then the dx's simplify out, and I have du equals 16 times x to the 15th dx. Okay. But remember, what I have up here is x to the 15th times dx, not 16th x times x to the 15th dx. So x to the 15th dx would just equal 1/16 du. And so now this integral becomes this integral. And that looks like a much nicer integral. Are there any questions up to this step here? Okay. Can you see how I show my work? Usually when I think it's best when you do math problems to work vertically. Okay, I'd like you to work vertically. I know in English we write sentences, and I've seen students do math where they work across. And of course, like in a solution manual, they'll have the work going across. You know, they'll have the steps going across. But as a human, when you do your work, it's much easier to follow if you work vertically. How many maybe have noticed that in just from their math experience? Okay, Jacob knows what I'm talking about, and let me see here. Hold on. Let me see here. I'm trying to find where. One moment here. Yeah, so where's my most recent? I know people participated here and chatted things. I'm trying to find where the most recent chats are. Well, I'll thank you everybody who answered there. Okay, so the integral then will equal 1/16 times the integral of the sine of u du, and the antiderivative of sine is minus cosine, and so my integral is going to equal negative 1/16 times the cosine of u plus a constant. Now, if you type that in WebAssign, would WebAssign accept this answer here? Would WebAssign accept that answer? Is that the right answer? I mean, are we done?
No, you have to substitute x to the 16th back in for you.
That's right, Maria. That's right. Very good. And so I'll do that. I'll go to the next page, but want to make sure I'm pacing myself correct. Correctly. All right. May I go to the next page? All right. Go to the next page. And okay. So the antiderivative, then, I put the x to the 16th back in, as Maria suggested. And so my antiderivative of x to the 15th times the sine of x to the 16th is simply negative 1/16 times the cosine of x to the 16th power plus a constant. Please let me know if you have any questions. All right. How many like this substitution approach? How many think it's kind of cool? Okay, seeing a lot of positive responses here. Thank you, thank you. Oh, okay, now I can see. Okay, I can see. See, I was trying to, like it used to be, they've upgraded Blackboard, and it used to be I could see like who's saying yes in the chat window, but there's another. I'll have to figure out how to do it, but I can see it like in the participants thumbs up, so that's good. Okay, well let's do another one. Let's do another one here. Oh wow! Now this is a definite integral. Okay, this is a definite integral. So there won't be any constant of integration on this one. Okay, let me give you a moment to copy this down. Okay, so this is interesting. Okay, well, what makes this problem, like, what's the, I always think, for substitution, we have to figure out what substitution we're going to make. And generally, what guides me is what's kind of what makes the problem difficult? What makes finding this antiderivative, well, we got to get the antiderivative. What makes it difficult? So what do you think's like the hard part of the problem?
The square root.
The square root. So what do you think we might want to try letting u equal to?
1 plus 3x.
1 over the square root of u.
1 over the square root of u might be a little bit too ambitious. We want to be very simple. Okay, and I appreciate all participation. Okay, not saying it won't work, but why don't we try this? 1 over the square root of u. Square roots kind of make life hard a little bit. Why don't I just let u equal 1 plus 3?
I mixed up my terms. My bad.
No problem, Samuel. No problem. No problem. Okay, well, let's go to the next page. So, okay, we're going to let 1 plus 3x equal u.
Professor,
Okay. Yes, Sophie.
I have a question. So, to my understanding, having a square root of something, you could like not cancel it, but like maybe express it by raising it to the 1/2 power.
Oh, definitely.
So could you do that to like further simplify u instead of having the square root?
Well, indeed, I will be taking that square root.
Uh-huh.
Well, the thing is, I want to be a little careful here. Ultimately, when I have like square roots or cube roots or fifth roots, whatever roots I have in a problem, like when it comes time to get antiderivatives, I do write the roots as powers.
Mm-hmm.
So like this, the square root of u will eventually be, I will eventually be writing that, if need be, as a power. But right now, it's sort of like I'm relying on my faith, so to speak, my math faith, I guess you could call it. If I let u equals 1 plus 3x, let's see what happens.
Okay.
But definitely we're gonna do that later on, Sophie, for sure.
Thank you.
Okay, you're welcome. So okay, u equals 1 plus 3x. Okay, u equals 1 plus 3x, and now I have to think about replacing x and dx, and also the limits too, because these limits 0 and 5, those are limits with respect to x. I'm turning this integral. I'm making a change of variable. I'm rewriting this integral as an integral with respect to u. So my x limits, I have to convert them to u limits. So a lot of changes here. Okay, well, let's see. Let's see what we do here. So, okay, well, we always say, you know, we have u equals 1 plus 3x. Okay, well, that means then that du dx is equal to 3. So du is equal to 3 dx. And that means dx equals 1/3 du. Okay, so the dx, I gotta have an expression for that in terms of u. The 1 plus 3x, I have an expression for that in terms of u, of course. And what's left is this x here. Okay, well, what we can do is, since u equals 1 plus 3x, that means then that u minus 1 would equal 3x, and so x would equal u minus 1 over 3. And so now I have an expression for x also in terms of u. So this integral with respect to x would be equivalent to this integral here with respect to u. Okay, and you notice that the 5 and the 0, well, let's look at the 0. The 0, that x limit now becomes a u limit of 1. Now, how'd that happen? Well, remember, u is equal to 1 plus 3x. So when x is 0, u is 1 plus 3 times 0. Right? U is 1 plus 3 times 0, and that gives you a 1. On the other hand, for the upper limit of 5, okay, when x equals 5, u is going to equal 1 plus 3 times 5. And that's 16. That's 16. So everything's accounted for, and now I have this new integral. Now I have this new integral to work with. The question is, will it work? Will it work? You know, it's like solving a puzzle, a little puzzle. Am I going to be able to solve this puzzle? Well, certainly, you know, I have here a third that can be brought out in front of the integral. And then there's a 1/3 here. Okay, a 1/3 there. Maybe I'll put it in red. 3 in the denominator means, in other words, this here, this is the same as 1/3 times u minus 1. So that 1/3 there, I'll bring that out in front of the integral. And so that gets me here. Of course, I'm going to have a 1/9 here. 1/3 times a 1/3 is 1/9. And okay. And the question is, all right, well, this u minus 1 over square root of u, would that be the same as u over the square root of u minus 1 over the square root of u. I mean, would that fraction
Yes.
be the same as this fraction? Maria thinks
Yeah.
it is, and yeah, definitely it is. If you think about it, think of it like this. If you had u over the square root of u minus 1 over the square root of u, you could combine those two fractions because they have the same common denominator, square root of u, and you would get this expression here. So this is okay, and that's going to be helpful. That's going to be helpful. Okay. Okay, so if there are no questions, I'll go ahead and move to the next page. Are there any questions at all? Okay. Go to the next page. Here we are. Okay, so, and you see how I keep everything together. Everything together. You have to be very, very neat with your work. Starting in, calculus 1, you should be neat with your work, but definitely in calculus 2, you have to be very neat because it'll help a lot. So, okay, now u over the square root of u, okay, well, u is the same as the square root of u times the square root of u. I can write u that way. And the square root of u times the square root of u over square root of u is just equal to the square root of u. And that's u to the 1/2 power. On the other hand, 1 over the square root of u, 1 over the square root of u is the same as 1 over u to the 1/2 power. And that's just going to equal u to the negative 1/2 power. So, wow, I can get the antiderivatives of these two functions. I mean, isn't it amazing what you can do if you try? All right. Are there any questions up to this step here?
I have a quick question.
Sure, Todd.
I'm just a little confused about how if you're making the square roots into the power of 1 over 2, then how come it's the same that for u to be the same as 1 in terms of
Oh, okay, all right.
making that the same?
I got you. All right, let's look at that. So you have u over the square root of u. That's the one you're questioning, right?
Mm-hmm.
So I think you'd agree we can write that as u over u to the 1/2 power.
Mm-hmm.
U I can write as u to the 1/2 power times u to the 1/2 power. That's okay, because when you multiply and the bases are the same, what do you do with the exponents?
You add them together.
Right. And 1/2 plus 1/2 is equal to u, or It's equal to 1.
Right.
So u can be written as u to the half times u to the half. Now, why would I want to do that? Well, because u to the half on the numerator and denominator cancel, and that gets me u then to the half power. That's how I got this term here.
Mm-hmm. And it works the same way for the 1 as well?
1 over the square root of u.
Yeah, u.
So for the second term, 1 over the square root of u is equal to 1 over u to the half power. But I can write that as u to the negative 1/2 power, because that's the definition of a negative exponent. When you have a positive exponent in the denominator, like you do here, if you bring that power up to the numerator, it becomes negative. Do you recall that from your algebra days?
Mm-hmm.
And that's how we get u to the negative half.
Okay, I see.
All right, very good, very good. And so, okay, and then we get the antiderivatives. So this is really just calculus 1. And then I have to put in the 16 and the 1. So I put 16 in, in this function here. I put 16 in first, and then I'm going to put 1 in for use next. And of course, I got to subtract the functions. I mean, this here is the antiderivative evaluated at 16, and this is the antiderivative evaluated at 1. And if you work that out, you have to be a little bit careful, but you're going to get 1/9 times 108 over 3. Okay, so I don't know if you I'm sure most of you have seen TI 8384 calculator. You can just type in, the 1/28 minus 8 minus 2/3 plus 2. You can type that in and then do like math frac. They use the math frac feature. How many have heard of that on TI 83 calculator? The feature where the math button, and then there's FARC feature, frac for fractions. Audra's heard of that. So, but these days, I know, I don't know if Desmo, I think Desmos could probably do that too, but at any rate, the 8, I mean, if I were to just maybe give a little detail, the 8 here, see, I tend to not to like to use technology. If I can do it with my mind, I like to do it with my mind, because it helps keep my mind sharp. 8 is equal to 24/3, and 2 is equal to 6/3. So the common denominator is 3. If you take 128 minus 24 minus 2 and plus 6, you'll get 108.
Professor,
So 108/3. Yes, Sophie.
just to clarify, how did you get from the second row to the third row?
You mean here?
I understand how you explained earlier how you simplified and you wrote u in terms of u to the 1/2 times u to the 1/2, because that essentially is 1. Yes, but how did you get correct? I see your arrow now.
Yeah, this is one of the integral rules that that you hopefully have seen in Calculus 1. It's the opposite of the power rule. So the 3/2 comes from taking like 1/2. Well, I want to be a little bit careful here. Let me just do the u to the half. Let me do that one. Okay, so the antiderivative, and maybe I'll use my stylus on this. Hold on. The antiderivative of u to the 3/2 du. No, that's u to the 1/2, right? Sorry. So that's going to be u. So let me ask Sophie. Normally, when you take the derivative, you subtract 1, right, on the power?
Correct.
Yeah. Well, for an antiderivative, you don't subtract 1. You do the opposite. You add 1.
Okay, I see what happened.
And then you have a half plus 1 here.
Mm-hmm.
That's the constant. And so you get u to the 3/2 over 3/2.
And then okay.
And then like 1 over 3/2 is 2/3.
Mm-hmm. I see. Okay, that makes sense.
All right, good question. One moment, class. One moment. Okay, pardon me, class, on that. What I'm learning to do is when like the phone rings, if it's a number I don't know, I like answer it and then hang up. You know, that way it doesn't keep ringing. You know, so you know, we're almost set for a break right now. So you know, this class, since it's a 3.5-hour class, we do take kind of a natural break when I want to give you some time to work on classwork. Now sometimes that might be 2 hours in, you know, but we are going to take a natural break here. Good question. Good question. Okay, so are we good then here? I'll go to the next page. So the integral is going to be 1/9 times 108/3, which equals 4. And so this integral is equal to 4. And this is you know, so all these examples show you the kind of work I want to see. So on your exams, I do inspect work. You know, I do like to make sure you're understanding the concepts. You know, that's I think a good thing. And are there any questions? All right, let me stop the recording.